Hello everyone, welcome to this webinar on exploring AutoML with Azure ML services. My name is Janakiram and I'm the speaker for today's session. So if you're attending the MI2 webinar series for the first time, this is a combination of two tracks. One is the machine intelligence and the other one is modern infrastructure. Machine intelligence is all about AI, IoT, edge computing, while modern infrastructure is predominantly about Kubernetes, microservices, serverless computing, and so on. Every other session that I do is from one of these tracks. And today, obviously, we are talking about the machine intelligence track, where I'm going to cover AutoML based on Azure machine learning platform services. So that's MI2. And coming to today's session, I'm going to kick off this with what is AutoML, and then an overview of Azure ML, specifically with focus on automated ML. And then we'll take a closer look at the process of building AutoML models through the Studio web experience, which is almost like a wizard style tool, which will help you train models without writing a single line of code. And then we'll also take a look at the Python SDK, which will give us a programmatic access to the automated ML platform. So let's get started. Traditional machine learning workflow includes multiple phases or multiple stages of the pipeline. It all starts with data acquisition, where we acquire data from a variety of sources, and then data exploration, where data is validated and evaluated for quality, and then it gets prepared to cleanse the data, transform the data, and make it useful for machine learning. And then the right set of features are identified, certain features are dropped, and ultimately we move into the model selection phase, where an appropriate model aligned with the data set and the business problem gets identified. And then the model training kicks off, which is the critical phase of this entire process. And once the model training is initiated, multiple hyperparameters get tuned. This process gets iterated multiple times. And finally, the model is used for inference or prediction. And multiple individuals, multiple teams, and multiple tools, frameworks, environments are used for each of these phases. Now, obviously, one engineer, one data scientist, or one developer, or one DevOps engineer cannot own this entire pipeline. So they have to specialize in one thing, and typically this is a team effort. So individuals with focus on each of these phases collaboratively work on training and data preparation, deployment, prediction, and all these phases. When it comes to AutoML, we can bypass all this and let the platform own most of these phases or the stages of the pipeline. So we only focus on two things when it comes to AutoML. One, data acquisition. We still need to get the data and do a little bit of validation, preparation. And once we have the data set in place, we can let the AutoML platform do the rest. And finally, we walk away with a model and even the deployment of the endpoint for online and batch inference. So it's a pretty efficient way of training machine learning models, even if you are not a seasoned data scientist or an ML engineer, or even if you don't understand GPUs and infrastructure elements of machine learning. So that is AutoML. You walk in with data, walk away with the fully trained model. Now, when we look at machine learning in the cloud, it can be easily compared to some of the evolutionary phases of the cloud itself. For example, there is IaaS in cloud, which is infrastructure as a service, where engineers deal with VMs and they are pretty much in the driver's seat. Similar to that, most of the cloud platforms expose virtual machines based on CPU and GPU infrastructure. And for this, you need to know a lot of DevOps, you need to understand provisioning, scaling, monitoring, and deal with a lot of infrastructure aspects of the cloud. For example, the data science VM, the deep learning VM provided by some of the cloud providers will let you spin up raw virtual machines and pretty much define the entire process in the fleet of VMs, either targeting CPU or GPU. Now that is the lowest level of the spectrum. Then we have platform as a service that exposes machine learning capabilities. And this is typically targeted at data scientists who don't need to worry about infrastructure, but predominantly focus on the training, tuning, and serving aspect of the machine learning models. So here, they don't need to deal with provisioning the VMs or Kubernetes clusters or networking aspects. Instead, they only focus on the high-level APIs that they can use from languages such as Python or R. Then we have the abstracted set of services, for example, Azure Cognitive Services, that deliver pre-trained models as APIs. Computer vision, natural language, speech synthesis are some of the examples of high-level languages that are available as just APIs. And for this, you don't need to know anything. You throw an image at the computer vision service, it comes back with the image classification or object detection output. Similarly, with speech, you can throw an MP3 file and come back with a fully transcribed speech to text output. And with language, you can perform translation and search and some of the other natural language specific capabilities. And then somewhere in the middle of platform and services, by the way, platform is very similar to PaaS, and services can be easily compared to the SaaS version of the cloud. And AutoML fits right in between. So here we have best of both. As data scientists, you get quite a bit of control over the data. You're basically not relying on the data sets used to train APIs like cognitive services that can only do predefined set of activities like recognizing or identifying celebrities or identifying objects that are based on popular data sets like Coco. But if you really want to bring your data and use some of the best and well-known models, algorithms to train the model, then AutoML comes in. So here, you don't need to know anything to do with ML. At the same time, you create custom models based on your custom data, and that is the beauty of AutoML. So when it comes to the advantages, as I mentioned, you can implement ML solutions without extensive programming knowledge or understanding the nuts and bolts of machine learning. Obviously, it saves a lot of time and resources because you don't need to do feature engineering, you don't need to do model selection, you don't need to do hyperparameter tuning. None of those are required. And all of that is left to the platform to decide. And of course, this process leverages the best practices of data science. So whether it is choosing the right algorithm or choosing the right parameter or some of the hyperparameters like how many epochs, what is the learning rate, how many layers, how many neurons per layer, and how complicated is your neural network. A lot of those decisions are left to the platform. And the platform does its best in terms of choosing this. And it provides a very iterative and agile way of solving the machine learning problems. Obviously, Microsoft is one of the pioneers when it comes to machine learning and developer tools. And when they launched AutoML with Azure, they focused on three aspects. One is classification. So classification is a very common problem in machine learning. Some of the examples include fraud detection. For example, every time a credit card is swiped, you can detect whether it is a legitimate transaction or a fraud transaction, and that is a simple classification. Similarly, handwriting recognition, because handwriting results in one of the alphabets. So obviously, we are going to classify whatever is written into one of the alphabets of a chosen language. And then object detection, where you can apply techniques like SSD to to detect multiple objects in a specific image and then come out with a very detailed tagging and classification. So regression deals with continuous data, for example, predicting housing prices, a very popular example, automobile resale value, and even performing anomaly detection. Time series forecasting deals with any data that is attached to a timestamp. For example, predicting sales forecast, demand forecast, and predictive maintenance of devices based on the time series data coming from the sensors are examples of time series forecasting. Now, all these are again classified into one of these three techniques of classification, regression, time series forecasting. So these are the three problems that you can solve by using AutoML of Azure. So how exactly does AutoML work? Well, there are three core aspects. The first one is you bring in your data set. Now, this data set is going to be the input. So obviously, it assumes that there is some level of quality associated with the data set. You can't bring in a broken data set with a lot of missing values and very inconsistent data points. Of course, AutoML will fix a lot of those problems, but your data set should be clean enough and ready for AutoML to kick off the training and parameter tuning. So that is the data set. And then you identify the target metric. So target metric is basically the label. For example, when we bring in the patient data set and we want to predict whether an individual is prone to diabetes or not. So the last column of this data set could be diabetic, yes or no. So that is going to be the target metric. And similarly, when we run a campaign to figure out if a customer is going to buy into the product, the target metric is the buy decision, yes or no. In linear regression, it could be the forecast. For example, how much is going to be the housing price based on the market conditions and so on. So we choose the target metric, essentially the label, and then we define certain constraints. For example, how long do you want the training and the AutoML job to run, and what is the budget that you want to allocate for this specific task? Because obviously you don't want to spin up a massive fleet of GPU cluster and run it forever. So you can apply some constraints in terms of time and in terms of cost. And AutoML will restrict itself within those constraints. So once we provide these inputs, then Azure AutoML will basically pick up three different permutations and combinations. The first one is called the featureizing technique, where it extracts the best possible features from your data set. And trust me, this is a big advantage, and it takes away a lot of pain of creating machine learning models. So it basically applies multiple techniques of extracting features from your data set. And then the second variable is the algorithm. So to solve a machine learning problem, there could be more than one algorithms, and we never know which would deliver the best yield. So Azure AutoML will consider all possible algorithms for the given regression, classification, or time series analysis data or the problem. So that is the second variable. The third variable are the parameters, and this is the traditional hyperparameter tuning. Again, as I mentioned, how many nodes should I use if it is a deep learning model? How many neurons per node? What kind of activation function should I use? What is the epoch? What is the learning rate? What is the optimizer? And how do I measure the accuracy of my model? So all these parameters can be tweaked and experimented to get the best possible outcome. Now, a data scientist will have to mix and match these variables. For example, you might apply a different featureizing technique and applying that to a different algorithm with a different hyperparameter tuning scheme will give you a better accuracy or a different level of accuracy. So you have to iterate over this multiple times to arrive at what is the most optimal model for that given problem. So AutoML does all of that automatically. So you don't need to deal with featureizing. You don't need to deal with choosing the best algorithm. And of course, you don't need to do hyperparameter tuning. All these three are basically experimented with multiple permutations and combinations to arrive at a leaderboard. So end of the job, you'll actually see a very nice leaderboard that is going to rank every model based on the score that you chose. And obviously from this, you can handpick the best and use that for your deployment and eventually for your inference and prediction. So that is the process involved in Azure AutoML. Some of the key features, as I mentioned, is automatic featureization. So feature engineering is a very, very important aspect of training machine learning models. How do you enable encoding of your features, and how do you basically transform these features for better accuracy? So it's a very involved and very sophisticated technique. If you don't optimize your feature engineering, you might either underfit or overfit your model. So which means it's going to impact the accuracy. Either it is going to be highly skewed towards giving you positive results, or it might give you lesser accuracy and lesser precision in terms of prediction. So feature engineering is very critical. Now, AutoML does featureization all by itself. And then there is a concept called ensemble models, where multiple algorithms and multiple parameters are being used. And then to the outcome of this, another machine learning model gets applied to handpick the best possible model from that. And Azure AutoML supports two techniques for the ensemble model. One is voting, the other one is stacking. So I'm not going to go into the depth of it. You can read the documentation on the intricacies of these ensemble models, but the idea is they will give you a mechanism to filter the best candidate from the outcome, AutoML outcome. The other important feature is you can use local compute target or remote compute target. So if you're actually using a smaller data set and a very simple problem, you can actually do it on your local machine. So Azure ML will still train based on AutoML, but your local workstation or your server could be the test bed, could be the workhorse for the machine learning job. But if you are bringing in a very sophisticated and very, very big data set, and obviously your local compute is not sufficient, then you can spin off the job on a remote cluster. And this cluster can be CPU based or GPU based. So I'm going to walk you through a demo where we will discuss this in more detail. You can use a wizard on the Azure portal where you don't need to write a single line of code. Or if you want to mix and match your programming with AutoML, like you want to perform some basic feature engineering and basic transformation before you kick off the AutoML job, you can use your favorite tool like Pandas, NumPy, scikit-learn before you hand off the process to Azure AutoML. So that is the advantage of using Python SDK. Obviously, there is a tight integration with Azure services. For example, the dataset is stored on Azure Blob, Azure Storage. Then the model is going to be packaged as a Docker container, and the image is going to be stored in ACR. The analytics are going to be integrated with the Azure monitoring services and log analytics. And then there is support for Onyx, which is the Open Neural Network Exchange, which is highly interoperable. AutoML can emit Onyx models by by the end of the training process. So all these are some of the unique features of Azure AutoML. Now, I want to walk you through two different demos with two different problems. The first one is going to be the Azure portal-based no-code AutoML. And then the second demo is how do we use the Python SDK. So let me switch to the portal and I'll show you how this actually works. So if you see my browser, I am currently on Azure portal. So it all starts by creating a resource group. For example, let me go to resource groups, and then I'm going to create a resource group. So let's call this demo, and I'm going to choose Southeast Asia. Now, once we have the Azure resource group, which is going to be the container for the ML workspace, we can go ahead and add an Azure ML workspace resource. So here, when we are adding a new resource, we'll search for machine learning and choose the machine learning resource. And there were two plans. Just a week ago, had you visited this, there was a basic and there was an enterprise. But at Ignite 2020, which concluded last week, Microsoft has basically merged both the basic and enterprise plans into one. Now there is no basic, there is no enterprise. They are merged and there is only one Azure ML. So you get all the features of enterprise with basic. Basically the difference has been removed completely. So you can now go ahead and create an ML workspace. So the workspace is going to be a container within the resource group that holds all the assets that belong to your machine learning project. For example, the data sets that you upload, the storage accounts that you create, the compute resources that you provision, the container registry, and then the Kubernetes clusters that you may use for training and inference. All of them are grouped under a workspace. So let's call this workspace ML AutoML demo. So, and then choose the region. Obviously, I'm going to target Southeast Asia. And then you can click on create. Now this is going to create a workspace. Now creating a workspace is the first step. It's pretty straightforward. It doesn't take more than a few minutes, and we can actually see that the AutoML demo workspace is going to be created in just a few minutes. But I don't want to wait. This is going to take a while, and this could just be staring at the screen. So what I've done is I've already gone ahead and created a machine learning workspace called bank marketing. Now, obviously, this is meant for one of the problems that we're going to solve with AutoML, and that is about a bank trying to figure out if any of their existing customers or who in the existing customer base are most likely to buy a term deposit plan, a term deposit product. So that is the problem that we're going to solve. So there is a data set that will give us historical data. And from that, we'll actually perform a simple classification task to figure out if a given customer is going to buy a term deposit product or not. So, so now the machine learning workspace is created. So we can click on launch now, the Azure Machine Learning Studio. Now this is going to be the tool that we're going to use. So this is a very nice interface and one of the best interfaces available in the public cloud to train the models. So on the left hand side, you notice there are notebooks, there is automated ML, there is a designer. I'm going to do a deep dive on this very soon. It's a pretty impressive drag and drop wizard, a canvas to train deep learning models. So these are the authoring tools, and then there are multiple assets like the data sets that you import, the experiments that you create, the ML ops pipelines that you're going to create, the models that get registered, and the endpoints that expose the deployed models. And then there are some resources that we're going to manage, like the compute, which is obviously based on Azure VMs or Azure Kubernetes service or Azure compute instances, Azure container instances, I'm sorry. Data stores, these are like registered data stores that can be versioned and managed within the workspace. So these are basically the Azure storage accounts that will hold your data sets. And data labeling, so you can again use this to label multiple data sets. Now we are going to focus on the automated ML. So when you choose automated ML from authoring section, you can choose what is called as the automated ML run. Now there are 3 steps if you actually see here. Select the data set and then configure the run. This is basically your job definition. And then the task type and settings. And then we are off to the AutoML job. So the very first step, remember in my slide, I actually talked about how you walk in with a data set and walk away with a model. That's exactly what we're going to do here. So it all starts by creating the data set. So we are bringing our own data set. So you can upload a file. For example, let's call this bank, and then tabular is the only choice that is available. Now, in the next step, you basically browse for your model, for your data set, and upload that. So here, I go to my data folder and pick up the data set that I want to upload. So that is the next step. So once we have that in place, let me pick up the bank marketing data set. So so this is now uploaded, and in the next step, we basically choose the features, the columns and the way it is getting passed. So here you actually notice that it has detected it is a comma separated or a delimited file, and then we can choose use headers from the first file, and it then shows the actual column names like ID, age, job, and so on. And in the last column we have yes or no. So Y is basically will the customer buy a terms deposit. So that is basically the schema and the file here. And then in the next step, we get a chance to look at schema at a much more detailed form. If you want, you can turn on and turn off certain features. For example, in our case, day of week is not really useful, so we will take that off from the schema. And then we go to the next step. So here, basically the details are shown where it is going to be stored and what is the basic information. And then you go ahead and create the data set. So now the data set is created. So we'll choose bank 1, click on next. And then here we can create a new experiment. So an experiment is basically like a science experiment. That's why it is aptly named as an experiment. So just like in a science experiment, you go through multiple iterations before you arrive at the desired outcome. In machine learning, we create an experiment and we run it multiple times with permutations and combinations. For example, with different featureization techniques, with different algorithms, with different hyperparameters, and we mix and match and we repeat multiple times till we get the best outcome. So that's why it is called as an experiment. So we will call this bank experiment. And then we need to choose the target column, which is basically the label, for our data set. So obviously we are going to choose the last column, which is Y, whether the customer buys a product or not. And then you got to, because you're using the Azure portal and you're creating an AutoML job from the portal, you can't obviously use the local compute. So now you have to create a cluster, a fleet, that is going to be responsible for running our experiment. So we'll actually call this bank cluster. And then you can choose whether it's a CPU based or a GPU based. if you are running complex data types and you want to run deep neural networks, then GPUs make sense. But for classical machine learning, and if you're not dealing with a large data set and you're not using deep learning, then CPU is good enough. Then you choose one of the VM types. So Azure has a very, very comprehensive set of configurations and family of VMs available. So you can choose that. And then you can define the minimum number of nodes and maximum number of nodes. Now, this can be 0 because if there is no activity and if there is an idle period, for example, 120 seconds, the Azure ML will automatically shrink this to 0. That means you don't have a compute cluster running all the time. If this has not been running for a while, it automatically becomes 0, and that will save you a lot of costs involved in running VMs. So we choose the basic settings here, and then what we're going to do here is click on okay, give me a second, I want to hide this. So again, to save time, we already have a compute cluster created exactly the same configuration. So we click on next, and then here again you can see there is a classification task to predict one of the several categories like yes, no, blue, red, green, and so on. If you want, you can enable deep learning. Then there is regression, predict continuous numeric values, and time series forecasting based on values that are time stamped. Now, this can also be deep learning enabled. Now, we choose classification because we have a binary classification problem here. We are predicting yes or no for a given customer. So we choose classification, and then we look at the additional configuration settings. So you can choose what metric AutoML uses to decide on the ensemble leaderboard. So here you have accuracy, the baseline parameter. You can also go for AUC weighted, average precision score weighted. So all these are techniques to basically evaluate how effective and how precise and accurate your model is. So we choose AUC weighted, which is actually good for classification, particularly when you have a smaller data set. And then you can also enable explainability, which will tell you why a specific model has been chosen. And if you think certain models don't make sense, you can actually blacklist them. So you can block those algorithms from being used by AutoML. So if you see the kind of algorithms used here, there is logistic regression, which is plain vanilla regression based algorithm. Then there is the SGD, the stochastic gradient descent based regression. There is support vector machines, there is linear SVM, there is k nearest neighbor, decision tree, a lot of options here. And what it actually means is if you don't block any of the algorithms, Azure AutoML will effectively use all of them to figure out the best possible model from this list of available algorithms. Exit criterion will define how long your job will run. You know, if there is no desired outcome, it may run forever. So you don't want to run into expensive bills. So you'll actually say that, you know, run this for 3 hours and stop it irrespective of the outcome. And then you can also define what kind of a threshold is used for terminate the job, right? For example, when my AUC weighted average reaches 0.8 or 0.9 or whatever is the actual metric that makes sense, I input that, and that will be one of the criterion used for terminating the job. Now, you can also define the validation. So there are multiple techniques to validate a model. You can choose that. Concurrency, how many concurrent iterations are run. This will directly impact your cluster auto scale. You know, if there are concurrent iterations that are consuming more CPU cycles, it will automatically expand your cluster. So that's the additional configuration. And then we finally click on yes, finish, as simple as that. So going back, what we have done is we chose the data set, we configured the runtime parameters like the remote compute and the configuration of that. And then we chose the task type, and we provided some inputs on what is the termination criteria, what does accuracy means, what does accuracy mean, and what metric is being used to evaluate the leaderboard, and so on. And once we click on finish, this job kicks off. And it might take anywhere from an hour to a few hours for this to run. So obviously, I'm not going to keep you staring at my screen. So I have already trained an AutoML experiment, or rather a model. So it is called Bank AutoML, and this is my experiment. And one job is already completed. And within this, there are multiple runs. So here, I actually trained this today morning. So you can see that the data set is coming from this. This is the ID of the data set. And if you go back, you'll actually notice that it's the same banking data set that we used. Data set is registered as bank. And then you can look at how this this data set looks like. It's exactly the same one that we have seen in the beginning. So that is the data set. And then this experiment uses the data set that we have seen, and then the best algorithm that it has used is voting ensemble. That is the algorithm that it used to create the final model. And as you can see, this has a pretty good accuracy. So this is the best model. Now you can also look at the number of models and their metrics by clicking on the models. We are currently inside the experiment, and we are looking at one of the test runs we made under this experiment. So you actually notice that this is the best model, obviously with the top score. Sampling tells how many rows or what is the size of the data set. It used 100% of our data set, and it only took 1 minute 37 seconds to train the model, which is pretty good. And the other algorithms were also pretty decent. If you actually see their AUC weighted metric is above 90%. Now, if you're wondering, some of these algorithms actually have two different names. So this is logistic regression, and then this is the featureizer, standard scalar wrapper. So for this specific algorithm, Azure ML used a different featureization technique to train the model. Now, similarly with SGD, it used max absolute scalar. So multiple featureization techniques combined with multiple algorithms and different hyperparameters is what is considered for the ensemble. And obviously here in the leaderboard, this is the best model, and you can actually look at the explanation, and it will tell you a lot of details about why Azure AutoML has decided that this is the best model. So you can actually perform the exploratory analysis of the model. So once we decided to go with this model, you can choose this, right? So for example, you can go to you can go to the model here. So you can look at all the models that are trained. So we choose the first model, and then you click on deploy. So when you deploy, what you're essentially doing is you're taking the trained model and exposing that as an endpoint that is ready for online predictions and inference. So here you have two choices. You can host your model on an Azure Kubernetes service cluster, or if you are doing it for dev test, you can actually run it on an ACI instance, Azure Container Instance. So obviously this is going to package your model into a Docker image, throws that into an Azure Container Registry, provisions the AKS or ACI compute resource, and then deploys your model, the containerized model, and then exposes that as a REST endpoint. So you can choose what kind of authentication you want to use. So token or key-based authentication. So again, to save time, I have gone ahead and deployed a model. So if you actually see, I have registered the model. So this is the model that's already selected and registered with Azure. And there is an endpoint, and this endpoint is called bank infer. So what I've done is I have basically published this as an ACI endpoint, Azure Compute Instance, and it's currently healthy. So it is now available at this endpoint. Now, if you really want, you can also explore this Swagger URI. This gives us a lot of JSON data. You can take this and put it in a better tool to analyze what kind of an input is expected and what kind of an output comes out of this service. And then if you want to consume, there is a key that you can use with curl or any language, including Python, Ruby, Java, C#, anything that can basically invoke a HTTP REST endpoint. By the way, you can also use curl or the CLI from PowerShell to basically invoke this. So here is the URL, right? And this URL is now ready for online inference or online predictions. So now let's actually go ahead and invoke this model. So we have gone through a complete cycle. So here is the data point that I want to send to my inferencing service, right? So we are actually sending the details of someone with age 33, blue-collar employee, married, and there are a lot of other features that are used for training our model. We haven't mentioned whether this guy is willing to buy or not. In fact, that's what we want as an outcome of this prediction. So we take this, format that in a nice JSON format. So this is basically a JSON payload with an array, and it has multiple elements. In our case, we only have one. So this is stored in data.json. Now I use curl to invoke this endpoint with this bearer token, and it should come back and tell whether this individual is going to buy a campaign from the bank or not. So let's actually first set this environment variables, and then let's invoke curl from this, and the result is no. That means this gentleman is not going to buy into the bank's term deposit product. So this is pretty cool. We have gone from uploading the data set to performing the invocation of the inference endpoint without writing a single line of code, not even one line of code. This is almost like a wizard to train the model, and it is very powerful technique to train models based on your custom data sets with enough control, because you get to choose quite a few things, like what kind of algorithms you want to exclude, what is the metric that you want to measure the accuracy of your model, and what is the exit criteria. A lot of those things put you in control. It is not like a black box. But the beauty is, even if you don't understand the nitty-gritties, the nuts and bolts, the feature engineering, the the ROC curve, the AUC weighted metric, and the jargon that is typically used by a data scientist and ML engineer, you can still build a very sophisticated and a very precise and accurate model that is available for you to be integrated with your applications. Now we can turn this endpoint into a nice, cool mobile application and give it to a field employee of the bank, who will go ask the customer for some details, and he'll hit a button and it will tell whether he should pursue this opportunity or he should just walk away. So this is going to be like a big time saver for the marketing guys of the bank. So this is a live application, and the best thing is you haven't written a single line of code to achieve this. So that is the power of AutoML. All right, so now this is done. The next thing that I want to show you is how do we consume AutoML from the Python SDK. So I hope you are still with me. So let me switch to my other browser, where I have Jupyter notebook. And this Jupyter notebook is running on my local computer. So if you actually see, it is running on my local machine. So I created a virtual environment for Azure ML SDK. So I've already gone ahead, installed the Azure ML SDK with pip install. And then I'm going to use the Python SDK to basically train my model via AutoML. So I don't use scikit-learn, I don't use TensorFlow, I don't use PyTorch, I don't care about any of those. I simply do basic data upload and wait for the model to become available. So here in the very first cell, we actually import all the required libraries from Azure ML Core and Azure ML Experiment, AutoML Config, and all of that. So this is basically the API exposing the Azure AutoML platform in Python. So once we import all the libraries, then we load from the configuration. So if you actually look at the configuration, it is pretty straightforward. So my subscription ID, my resource group, and the workspace name called diabetes. It's already existing in my Azure resources. So I can actually show you this. So when we go back to home, when we click on diabetes, this is the ML workspace that was created, launch now. And this is the workspace that I'm leveraging from my Python notebook. So we load this into the environment, the workspace configuration, and then we are using the popular Pima Indian diabetes data set, which will take certain features like whether the individual is a pregnant, what is the skin tone, what is the age, and so on. And based on that, it will predict whether this individual is prone to diabetes or not. So we turn this into a data set, a data frame, and we upload the data frame, the entire data set to Azure Blob Storage. So in this step, we are basically reading the CSV file into a data frame. Think of it like a pandas data frame. And then we upload the entire data set from our local machine to Azure storage. So that is the next step. So you can actually see the output here, uploaded file to Azure storage. And then we go ahead and create a compute resource. And this compute cluster is responsible for running our AutoML job. Just like we use the portal to create a cluster, we are using the API to provision the same. So we define the min nodes, we define the max nodes, the VM class, the type of Azure VM, and then wait for completion, the timeout, the minimum node count. So basically whatever configuration we chose at Azure portal is now available through the API. So if that is already provisioned, it will basically reuse that. And that's what is the if condition here, or rather the try catch. Then we define the AutoML settings. So we'll say iteration timeout minutes, number of iterations, what kind of featureization you want to use. If you've already done feature engineering, you can turn this to off, which means Azure will not apply automatic feature engineering. And then iteration timeout minutes, how long do you want to wait for each iteration, and number of cross validations. So all these are the inputs to the AutoML job. Then we bring everything together. Basically we define what kind of a task we want to run. Obviously this is a classification task, whether an individual will get a diabetes symptom or not. So there is a classification. Path to the project folder, because we are going to dump some logs locally. And then this is the training data set. And this is the target compute where the job is going to run. The label of the column, the label of the data set, which is the class. And this is going to be used for the final prediction. And then we pass the AutoML settings, the entire parameters that we populated here. And that's it. Once we have the AutoML config, we will kick off an experiment and run the experiment with the configuration defined here. And as soon as we kick off this, it is going to basically transfer the entire job to the remote cluster. And then here you can actually see that there are multiple jobs that are used. So I can say 50. So again, just like the way we have seen this in the portal, basically it used 19 different techniques, or rather algorithms and feature engineering combinations to come out with the best possible model. So again, I got 77% accuracy. Not ideal. We can easily reach 90, but that means I have to go back and modify a few things here. For example, the primary metric, should this be accuracy or it should be the AUC weighted metric, right? So I can do some basic stuff here, and then this will become better. But without any modification, with baseline configuration, we got 77% accuracy, which is not bad. And then this is the best possible model. Now you can also look at how the accuracy has kind of fluctuated during this entire experiment. And once this is done, I can retrieve the best possible model, the voting ensemble, which is basically the best one, and then go to the next step of registering the model and then exposing the model as an endpoint. And after that, we can use curl to hit the endpoint and perform predictions. So this is AutoML from the Python environment, from a Jupyter notebook. And as you notice, we are not using any of the frameworks like scikit-learn, XGBoost, or TensorFlow, Keras, PyTorch, nothing. We don't need to deal with any of those. We simply grab the data set, upload it to Azure storage, spin up a compute cluster, define the job, and then tell where the data is and where to run the compute job, wait for about half an hour, walk away with the model. So that is the beauty of AutoML, whether you do it from the portal or whether you run it from Python notebook. You actually get a lot of power without knowing the intricacies and the internal details of how to train machine learning models. So that is AutoML for you, and that brings us to the end of this session. So we have seen both the no-code version of Azure AutoML and then the Python SDK. So that concludes the session. Thanks again for attending this, and I want to thank our sponsors, Google Cloud, the new stack where the content gets published in the form of tutorials and guides, Foghorn, an edge computing company based in Silicon Valley, Portworx, a container native storage company based in Bay Area. Thanks to them for supporting me with the resources and everything that I needed to run this webinar series. So this is going to be uploaded to the YouTube channel, and stay tuned for my next webinar. And I'm going to talk to you about how do we run ML inferencing in serverless environments with AWS Lambda. So that's going to be the next session. Stay tuned. Thank you. Stay safe. Take care, and I'll see you in my next webinar.